All right. Welcome back, everyone, to week 5 of the discussion sessions. So, we will begin today from where we left. And in the last week, if you remember, we were looking into the topic of heat generation in slabs and cylinders. In particular, we looked into the fact that if there is a heat generation source, which is uniform, of course, and constant, then what is its implications on the generic temperature profile of slabs. And also we looked into one case where the geometry was a cylinder with an annulus of inner radii R1 and R2. I think it was Ri and R naught, or R1 and R2, whatever you finite convenience. Okay, so so basically what we saw is that the major difference from the 1D heat transfer without heat generation and to the fact that if there is heat generation is lies in the fact that the temperature profile is no longer linear, which we saw in the case where there was no heat generation. But in case of heat generation, specifically in slabs, we saw that the temperature profile was parabolic in nature, and we solved a couple of problems involving that particular concepts on slabs. Thereafter, we solved, almost solved actually, one particular problem where we used this fact in cylindrical geometry, where if you remember, we said that there was a cylinder of inner radius R1 or an outer radius R2, and there is a heat source which is generating heat with some magnitude Q dot. It was given in the question that the exterior surface of the cylinder is insulated, and also it was maintained at a temperature Ts2. Given this information, they asked us to first evaluate, start from the heat diffusion equation and solve for the temperature profile, and then using the appropriate boundary condition we evaluated how T as a function of R would look like. This indeed came as a function of Ts2 Q dot and the material properties K, which also depends showing dependence on R2. And yeah, so this is how the temperature profile look like when we basically substituted the boundary conditions to evaluate the constants. And then they also asked us one more thing, which is to calculate the heat removal rate per unit length of the tube. And then we saw that the heat removal rate per unit length of the tube is equal to the heat flux. So basically we need to understand that the only way heat can be removed from the cylinder's body is by the cooling fluid that is flowing through his annulus. Okay, so because the exterior surface was insulated, so there was no way heat can escape from the exterior surface. So whatever the heat that is being generated inside the cylinder, that is to be dissipated radially inward to the flowing fluid, which is flowing with some heat transfer coefficient H and temperature T infinity. So what we did in order to find out the heat removal rate is to evaluate the flux at the inner surface. For that, we applied Fourier's law, and then they asked us to calculate the flux per unit length. So we just calculated the heat removal rate. They asked us to calculate the heat removal rate per unit length, for which we evaluated the flux using Fourier's law and then multiplied by the circumference of the cylinder at R equal to R1, which eventually gave us the heat removal rate. Just a second. हेलो. हाँ भैया. नहीं नहीं भैया, मैं एक काम कर रहा हूँ, मैं क्लास में हूँ, आप मम्मी से ही ले लीजिए, ठीक है, उनसे ही ले लीजिए. ठीक है, हाँ हाँ. Sorry for the interruption, there was a problem in the network, I'm sorry for that. So yeah, so so what I was telling, the fact that since we knew flux from the Fourier's law, then in order to calculate the heat removal rate, we just need to multiply it with the perimeter of the inner surface basically, which gave us an expression for the heat removal rate in terms of the heat generation Q dot and the radii of the inner and outer, I mean the radii of the cylinders, that is the inner and outer radius. Now, one important thing that I asked you to do is to apply energy balance now, considering the fact that whatever the heat that needs to be generated has to be dissipated out. Then apply energy balance, and I asked you to basically come up with the same form of answer if you simply apply energy balance at so if you choose a control volume such that it just takes care of the cylinder, and then if you apply energy balance in this control volume, then you can also show that your heat removal rate per unit length will simply come out to be exactly same as the one that we calculated using Fourier's law. Okay, so I believe you have done this, but if not, like, it's just very simple. Just use the fact that you just use the law of conservation of energy, that E dot in minus E dot out plus E dot gen is equal to 0 because it's a steady state. Then E dot out basically becomes become equal to E dot gen because E dot in is 0, and from there you can show that this is the heat removal rate. So basically you could have write E dot out as this times L, and then in the generation there would be pi times Q dot into R2 square minus R1 square, and there's a minus with an L, and this L and L would eventually cancel out, and with just, you can see that you will just simply get this answer as well. It's a straightforward thing. I hope now at this point at least, covering 4 weeks, you are in a good position to apply the energy balance. Okay, but here we were asked also one more thing, which I will show it today. That if you remember, we also need to evaluate something which is known as the heat transfer coefficient. So it says in question number 4 that if the coolant is available at T infinity, that is the temperature of the coolant is now given to be equal to T infinity, then obtain an expression for the convection coefficient that would be maintained at the inner surface to allow the operation to be prescribed at Ts2 and Q dot. So what they are saying now is that in order to maintain this operation of generating heat at Q dot and maintaining the outer surface of the cylinder at Ts2, and if there is a cooling coolant that is flowing possessing temperature T infinity, then what should be the value of the heat transfer coefficient? That's what they are asking. So for that, it's easy to calculate. So again, we'll be using the fact that at interfaces fluxes are continuous. So what I will say that, so what do we need? So we need to calculate the heat transfer coefficient of the, so this is heat transfer coefficient of the cooling liquid or the cooling fluid, which we will call it as H. And for this, what we need to do is we just need to say that my flux due to conduction at R equal to R1 should be equal to the flux due to convection at, sorry, I should have written is Q double prime due to convection at R equal to R1. So this is just applying flux continuity at the interface. We have done this many a times in the course of our discussions. So this is just flux continuity. Again, this is because of the fact that there is no phase change taking place at R equal to R1, which is the case here. Okay. So then we can write that if I multiply the left hand side and right hand side by L, I can just say that this is Q conduction evaluated at R equal to R1, and this times L, which is the length of the cylinder, then this becomes Q convection at R equal to R1 times L, of course. But this term, this is just the heat removal rate which we just now calculated, which we calculated in the previous exercise. That is just Q prime, right? So this becomes Q prime. This is just Q prime because we are multiplying flux with length. So this becomes heat removal rate per unit length. That's why this becomes Q prime conduction. And we already know its value to be equal to minus of pi times Q dot R2 square minus R1 square. Okay. So this is Q dot conduction. And then this is equal to your, so this becomes, so this is the heat removal rate due to conduction. So this then becomes heat removal rate due to convection. Okay, that's of course the case because this is flux multiplied by length, so its unit is basically watt per meter square times meter, which basically becomes watt per meter. So that's why this is the heat removal rate due to conduction, because this was heat flux due to conduction. Then multiplying by length implies that we are now seeking to calculate the removal rate per unit length. So that's why this is heat removal rate per unit length of conduction, and this becomes equal to the heat removal rate per unit length due to convection. Okay, and then we are using the fact that whatever the heat that is being removed by conduction is equal to the one that will go by convection to the other end of the fluid, basically. Okay, so, but as I said, we know that this value, that Q dot Q prime conduction is basically this value, right? Because this is the heat removal rate due to conduction that we calculated from the Fourier's law. Okay, that is the heat removal rate per unit length due to conduction, and we know that this is equal to minus of pi q dot, and then this is r2 squared minus r1 squared, and then this is, so what is the heat removal rate due to convection now? So this is the heat transfer coefficient times, instead of area, now it will become the perimeter, which will be 2 pi times r1. Again, the logic is same, because this is, so usually what we would have written is it is HA delta T, but now what we are doing is we are sorry, ideally what we have written is the flux is H times delta T, that is the convection flux, but since you are multiplying, since whatever what you are doing is you are calculating the removal rate per unit time, so that's why we need to consider it the perimeter uh, times, delta T, which is basically Ts1 minus T infinity. Okay, so so that's it. So from here you could easily get the expression of H. I hope this is clear. So if you are not, so this quantity is the heat removal rate per unit length due to conduction, which we have already calculated, and this basically becomes equal to the heat removal rate, heat that is being gained by the flowing fluid, because of the fact that the tube is, the cylinder is basically releasing this much of heat to the fluid that is flowing through the pipe. That's all that we are writing here. Okay, so from this you can come out with an expression for H, as because they're asking us to evaluate H. So but we can still cancel something, so this pi and pi gets cancelled, and then I can write H as what? I can write it as minus q dot times r2 squared minus r1 squared divided by 2 times of r1 times ts1 minus t infinity. Okay, so that is the heat transfer coefficients. But if you pay a closer look, uh, what we can see here is, let's see what we can see. So uh, one more thing we can do. So basically what we are doing is, since you are calculating heat transfer coefficient, you can actually calculate the modulus of this heat removal rate, because that's the amount of heat, or I would say you are considering the modulus of this q dot prime. This is actually the amount of heat that is being released from the cylinder. So here the direction is not that much important, because we know that anyway the heat transfer coefficient is a positive quantity. So in a way we are actually writing the amount of heat that is coming out, that is basically removed from the cylinder, is equal to the amount that is being taken to the that is being taken by the flowing fluid, and that's the reason why you are considering a modulus. And if we consider this modulus, this basically will become plus sign, and then heat transfer coefficient becomes plus sign, because there is no sense of telling that a fluid has a negative heat transfer coefficient. Okay, so that's the reason why we are considering the modulus. You can basically interpret this as the heat loss by the pipe is equal to the heat gain by the coolant, and that's exactly what we are writing it here. Okay, so that's the heat transfer coefficient. But one more important thing that you need to understand, that ts1 is not known. Okay, so for that we will use the fact that we already know the temperature profile, so we'll just substitute r equal to r1 in the temperature profile, because we know that this is how the temperature profile essentially look like. So this is the temperature profile. So what we'll do is, in order to calculate ts1, we'll basically substitute t at r equal to r1, and this will just be equal to ts1. So all we need to do is just substitute r as r equal to r1 in this expression. So I hope you can do this. It's very simple. uh, if not, I'll just write it here. So ts1, which is actually not directly known, is but it is known from the temperature profile, because this is just t at r equal to r1, and then if you calculate, this becomes equal to ts2 plus how much, q dot by, I think, 4 prime. That's the 4 prime r2 square minus this. This becomes q dot by 4 prime 4k r2 squared minus r1 squared minus, I think this becomes q dot by 2k r2 squared by ln of, I think this becomes what? This was ln of r2 by r1, basically ln of R2 by R1. That's it. That is TS1. So that's TS1. And you just need to substitute this TS1 here to fully know the value of this heat transfer coefficient. Okay, so that's it. That's end this problem. I'll stop here for a couple of time. If there are any doubts, you can ask me. All right. If not, let's move now into the week five's discussion. So what we will so the agenda for today's discussion, as you can see from your screen, is heat transfer from extended surfaces, and they are also known commonly by the name fins. Okay, and today's discussion is basically about assignment 5 that you are going to solve in couple of days time. And please pay attention to these videos, because some answers will be, so I'll give hints for certain answers which will help you to solve the assignment. Okay, so so that's what we will learn today, is heat transfer from extended surfaces. So I think you got a chance to basically look at the lecture series of this week's, which again was on extended, which again, so it involves discussions on extended surfaces or fins. But before actually solving problems associated with these fins, I will give you a quick recap of whatever you have learned in the week's lecture, such that you can brush up your memory or your understanding uh, on extended surfaces. Okay, so as the name suggest, extended surfaces means, let's say there is a face, let's say of a, what to say, of a slab, uh, which is, let's say, of this form. Okay, and so let's say this is a slab, and this is basically the face of the slab. Okay, this is, let's say, the face of the slab. Okay, and what we want to do is we want to dissipate heat faster from this face. Okay, or in other words, like it would be more precise to say we want to increase the rate of heat transfer from this phase. So our objective is basically how, so the question we are asking is, how do we increase the rate of heat transfer from the phase. Okay, of course you can also dissipate heat from this from the other surfaces, but that is not the point of interest, let's say, for this topic. Okay, we are only interested, let's say, that given this phase, and let's say there is some mechanism which provides us the fact that we can only dissipate heat through this phase only. In that context, I'm asking you that how do we increase the rate of heat transfer from this phase, and one of the ways of doing so is by protruding a surface attached to this face. Like for instance, you can weld a surface, or you can weld, let's say, you can weld another surface, and you can protrude this surface from this face. Okay, that is one way of dissipating heat faster from this dashed blue surface. Okay, and this additional surface that gets protruded from the base surface, so we will call this surface as the base surface. You have already seen that in your lecture series. So this is known as the base surface, and the surface that gets protruded from the base surface, this is known as fins, or as the name suggests. So since there is one fin, we'll call it as fin, and as the name suggests, this is also sometimes called as extended surfaces. Because this is extended from the base surface, that's why this is known as extended surfaces. Okay. The objective again of using fin is basically to maximize the rate of heat transfer from the base surface. Okay. All right. Now, based on this discussion, what you have seen is that, so what we are interested, so we are basically interested that given we have a base surface, so a base surface is exposed to a certain temperature, and you know that this is known as the base temperature. Oops, sorry. This is known as the base temperature. And what we are interested in, given that we have an extended surface, how does the temperature distribution looks like in this extended surface? So that's what we are trying to see. Okay, so we are interested in looking forward in the temperature distribution of the extended surface, and you know that this temperature of the extended surface is generally written as theta, which is equal to Tx minus T infinity, okay, where T infinity is the temperature of the ambient air that is surrounding the extended surface. Okay, this is T infinity. Then, and we say, let's say it has also a heat transfer coefficient H basically. So then we say that the temperature profile in the extended surface is denoted by a variable theta, where you know x is basically the axial direction. So this is just the x. So by x I mean that this is the x direction that I'm considering. So the temperature profile in the extended surface or in the fin is governed by this variable theta, which is the local temperature minus the far field temperature surrounding the extended surface, or the temperature of the fluid that is surrounding the extended surface. In for example, in fins, let's say we are having fins and the cooling is taking place by air, then T infinity is nothing but the temperature of the ambient air. That's it. Now given this information, you saw that applying, just applying energy balance, the temperature, the ODE that governs how this theta varies with x is by using this ODE, which is d2 theta by dx2 minus m square theta is equal to 0. Okay, this is very simple. Just apply energy balance, and you will see that you will end up getting this expression for theta. Okay, I hope this is clear up to this point. Okay, I hope this is clear up to this point, that the temperature distribution inside, so you need to understand that this theta is the temperature distribution. This is the temperature distribution of the extended surface of, or fin basically. This is the temperature distribution of the fin. Okay, and the ODE that governs the distribution is just d2 theta by dx2 minus m square theta is equal to 0, where you have seen that m is a parameter which is equal to under root of pH by KAC. Okay, where P is nothing but the perimeter of the fin, H you already know, that is the heat transfer coefficient of the ambient fluid. This is the heat transfer coefficient of the ambient fluid. K is the thermal conductivity of fin. And AC again is the property of the fin, it's the cross-sectional area of the fin. Okay, so this is the cross-sectional area of fin. Okay, so you saw that in M there are actually three fin properties. For instance, the perimeter of the fin, the thermal conductivity of the fin, and the area of the fin. And it also depends on the heat transfer coefficient of the ambient fluid, that is H. Now, given this, you encountered, so what we'll do is we'll always specify at x equal to 0. So now you can understand that if I basically start my x axis from the point where the fin had started, you can realize the fact that at x equal to 0, your theta is, so what will be theta at x equal to 0? Theta will be just Tb minus T infinity, right? Because we know that that at x equal to 0 we have encountered, so at x equal to 0 we will reach the base surface whose temperature we already know it is equal to Tb. So then theta at x equal to 0 becomes theta b, which is Tb minus T infinity, and we'll call it as theta b. Okay, but depending on the boundary condition that you apply on the other face of the fin, there are expressions that dictate how the heat transfer from the fin would look like. For instance, if I have a long fin meaning that if my length of the fin goes to infinity, I can say that this you have already derived in your theory classes, that you just need to solve this ODE and then apply the first boundary condition, which is this, and then apply the other boundary condition which says that my length of the fin goes to infinity, and then you can eventually calculate that your rate of heat transfer from this long fin is equal to square root of PHKAC times theta b. Okay. Similarly, instead of having a long fin, if you use the fact that the tip of the fin is insulated, this is known as insulated tip boundary condition. You have seen that. So this is for the long fin. Okay. Similarly, if you use the fact that the tip of the fin is insulated, tip of the fin is insulated, you can eventually show just by solving the ODE that you just now saw, that your Q dot, we'll call it as Q dot INS, which is the insulated tip boundary condition, as under root of PHKAC theta b times 10 hyperbolic ml. Okay, where L is the length of the fin. Okay, so depending on the boundary condition you apply at the tip, your rate of heat transfer, your prescribed, or the calculated rate of heat transfer from the fin, the functional form would get altered, would basically get altered. For instance, in case of long fin, this is something that you see this factor will remain the same, okay, under the PHKAC theta b. The only things that will change is the prefactor that will come after this factor. Okay, you can also have a boundary condition, although I'll not, for the sake of brevity I will not show it here. You can also have a boundary condition where there is convection taking place from the tip of the fin in addition to the convection that is taking place from the lateral surface. In that context, your expression for your q your expression for your q dot will get altered, okay, accordingly. Okay, so there are different, I think there are 4 conditions that were stated to you: long fin, insulated tip boundary condition, convection from the tip, and the fourth is prescribed temperature at tip. For instance, if I say that my temperature at the tip surface is just equal to, let's say, theta 1, which is, so theta 1 will be just T1 minus T infinity, where T1 is the prescribed temperature at the tip. In this context also, okay, your expression for the rate of heat transfer from the fin would change, and that prefactor, as I was saying, will basically get altered. Okay, so the other 2 conditions you have already derived, or this is available in your prescribed book of in your prescribed book for the course. You can look into your textbook for the other 2 tip boundary condition. So the bottom line is that depending on the tip boundary condition, your expression for the rate of heat transfer from the fin surface will get changed. Additionally, you have seen another 2 important things, as I would say. The first one is known as fin effectiveness. And we will denote it as epsilon f. And this effectiveness is actually defined as rate of heat transfer from the fin to the rate of heat transfer without fin. Okay, so effectiveness actually says that how much effective we are in dissipating the heat to the ambient when you are installing a fin. That's it. That's another way of interpreting fin effectiveness. Okay, so this is known as I said, this parameter is known as fin effectiveness, that I just now show it here. There is one more parameter which is known as fin efficiency. Okay, and we generally denote it as by eta f, and this is known as q dot fin, that is the rate of heat transfer from the fin to the maximum rate of heat transfer from the fin. Okay, now we will see that what is this maximum rate of heat transfer from the fin, although I think we have got a glimpse in your lecture series, but we will see this when we solve a problem involving this fin efficiency and fin effectiveness. But this is how the fin effectiveness and the fin efficiency are defined, and these two things are sometimes known as fin parameters, fin performance parameters. So So if you, let's say, go to the market and ask which type of fin is better, you need to assess two parameters, the fin effectiveness and the fin efficiency. Okay. All right. So this is the background information that I want to give to you before solving problems on extended surfaces. And and now I hope so just a recap, we looked into why basically do we install an extended surface or fins, and how and what is the ODE that basically governs the distribution of temperature from this fin surface. So you need to understand that what are the mechanisms that can dissipate heat from this fin surface. So one is by convection from the lateral surface, that obviously can happen, and one is from the tip. Now convection from the lateral surface will always be the same, but depending on the boundary condition we apply at the tip, we have encountered several forms of the rate of heat transfer taking place from the fin. For instance, if I have a long fin, that is the length of the fin goes to infinity, this is how we basically, uh, this is how we basically get the expression for in case of long fin. That is, what is the rate of heat transfer from the fin if the length of the fin goes to infinity. Okay. And then we have also looked into the insulated tip boundary condition, that is the what will be the rate of heat transfer from the fin when the tip is insulated. Okay. See, the logic is very simple. You need to solve this ODE, use the two boundary condition. One, this boundary condition is always fixed. The other boundary condition depends on what type of tip you have. And then two boundary condition, it's a second order ODE, just solve for theta. After you get theta, just apply Fourier's law. That's it. That will give you, the rate of heat transfer. That will give you basically these rates of heat transfer that we are talking about here. But I'm not doing this derivation because this had already been discussed in the lecture series. Okay. And thereafter, what we saw is like we looked into the fin performance parameters. For instance, we looked into fin effectiveness and fin efficiency and the definition of fin effectiveness and fin efficiency. Okay. All right. Now I think we are in a good position to solve a problem, and the problem is on your screen. You can have a look and think about how do we go ahead and solve this problem. I'll wait here for a couple of minutes for you to have a look at this problem. Okay. All right. So let's have a look at this problem. So it says that a long circular aluminum rod, it says that it's a long circular aluminum rod is attached at one end of a heated wall and transferred heat by convection to a cold fluid. Then they're asking if the diameter of the rod is tripled, how much would the rate of heat transfer change? Then they're saying that if a copper rod of the same diameter is used in place of aluminum rod, how much would the rate of heat removal change? Okay. So again, this is an ideal problem on fin. So it says that there is a heated wall. So it's like there is a heated wall. Okay. And in order to dissipate heat from this wall, you are attaching a circular long aluminum rod. You are attaching a circular long aluminum rod. Okay. uh, which basically takes in heat from this wall, from this heated wall, and then dissipate it to the cooling fluid. Okay, the cooling fluid has a heat transfer coefficient H. Okay, you may consider the heat transfer coefficient to be H, and of course if you want, you can also consider its temperature to be T infinity. Then what they're asking is that if I now triple the diameter of the rod, how much would the heat removal change? Okay, so this is exactly a fin problem because you are using an extended surfaces from an already prescribed solid surface. So the crux of the question is that they have said that it's a long rod. They have said that it's a long aluminum rod, and of course this is circular. That's what they have said. Okay, from this we can infer that we'll use the concept of long fin boundary condition. Okay, So, so if you remember, the long fin boundary condition says that the rate of heat transfer from the fin is just under root of pH KAC theta B. Okay. But here they are asking us only the dependence of diameter. So we'll try to write this. We'll try to write this rate of heat transfer as some constant times its dependence on diameter. So let's see from where diameter of the fin would come. So remember, P is the perimeter. So your perimeter will now just be equal to pi times d. AC is the cross sectional area of the fin. So that's why this will basically become equal to pi by 4 times d square. So this is from where we'll get the diameter. So we'll just put in the values here. So Q dot F will be under root of your perimeter is pi times d times the heat transfer coefficient k and h are just constants times your AC is pi by 4 d square, and then there is this root over times theta b. Okay, so you can see that Q dot F is proportional to d to the power 3 by 2. Okay, that is simply because there's a d square and there is this square root here, which will produce a dependency of d to the power 3 by 2, and rest you can just dump into the constant. Okay, so this means if my d changes from d to 3d, then I can say that the rate of heat transfer from the fin when the diameter was d1 to the rate of heat transfer from the fin when the diameter was d2, where d2 is basically equal to 3 times of d1, is equal to your d1 by d2, to the power 3 by 2. Okay, but we know that d2 is just 3 times of d1, so this will become d1 and 3 times of d1 because you are increasing the diameter of the second fin to 3 times to that of the first one. Then this becomes, so then what do you get? So then you will get is Q dot fin when the diameter is d2 is equal to 3 to the power 3 by 2 times Q dot fin when the diameter is d1. Okay, or if you just write it as, like, I think it will be better if you write it as Q dot fin when the diameter is d2 by the fin where the diameter is d1 is equal to 3 to the power 3 by 2. Roughly 3 to the power 3 by 2 comes out to be equal to 5.2. So you are enhancing the rate of heat transfer by around 5 times basically. So using a fin, okay, of diameter d2 where d2 is 3 times the diameter of d1, you are increasing the rate of heat transfer by roughly 5.2 or like 5 times basically. Okay, so that's the that's the first answer. Okay, so I hope you understood how did we do this. So the idea here is that it says that it's a long fin and it's circular in nature. Okay, so basically we then utilize the fact that for a long fin we know that the rate of heat transfer is just square root of pH KAC times theta b. Okay, had this been given that it's a insulated tip boundary condition, then there would be a factor of 10 hyperbolic ml that will come into the picture. Okay, and in this m also there will be a dependence on d basically. So then it becomes like a more like then this 3 by 2 will basically change to some other numbers. Okay, so as I said, depending on the boundary condition that you apply on the tip, okay, your rate of heat transfer from the fin would basically differ. Okay, and I hope you realize that when I say it's a long fin, that means that I am just saying that my theta. So I hope you understand this, right? This I have not clarified, but I thought that you already know this, because if I say long fin, it means that my theta at x equal to L, when L tends to infinity, is equal to theta infinity, which is just t infinity minus t infinity, which is 0 basically. So it means that the fin is so long that upon reaching this length L, all of the heat has been dissipated to the ambient, which means that the tip also has the temperature. So if this means that tip also has the temperature of ambient in case of long fin. That is the implication of the fact that theta at x equal to L is 0 basically. This means that, again I repeat, this means that upon reaching this length, the length is so long that all of the heat that the fin has been carried from the wall, this will basically dissipate from its lateral surface, and then in that context you can say that the tip of the fin is at temperature T infinity only, meaning that your theta, which is just the difference of T minus T infinity, will now be T infinity minus T infinity, because the tip itself is at temperature T infinity, which means theta at theta equal to at x equal to L is just 0 basically. Okay, that is the implication of long fin. So the boundary condition for long fin, I hope you realize that at x equal to let's say 0, theta is theta b, and this is at x equal to 0, and at x equal to L, your theta is basically equal to 0. So these are the two boundary conditions for long fin. So if you solve the second order ODE that we just saw and apply these two boundary condition, you will basically, and then use Fourier's law, of course, you'll basically get this expression for rate of heat transfer from a long fin. Okay, I hope you understand this. I was not telling this because I thought this had been already, because yes, of course, if you look into the video of this week's lecture series, you will see that this had been clarified and like discussed uh, in the lecture series. Okay, so the first part is done. In the second part, what they are saying is that now if I have a copper rod in place of the aluminum rod, how much would the rate of heat removal change? Now you need to understand that where does the dependence on material come into the picture. So the dependence on material will come into the picture from the thermal conductivity. Okay, which means now I can say that the rate of heat transfer from the fin, which was under root of PHK times AC times theta B, you can say that for the same diameter, I can say that Q dot of fin is proportional to square root of K, basically. Which means if I calculate Q dot of a aluminum fin to the Q dot of a copper fin, I will simply write K of aluminum by K of copper to the power half. And roughly K of aluminum is around 240, watt per meter Kelvin, and K of copper is roughly around 400 watt per meter Kelvin, which means that you can write that your copper fin will dissipate approximately 1.29 times the aluminum fin. Okay, that's that's the that's I mean, so this much heat, so this much times the heat removal from the aluminum fin will take place if you now install a copper fin of the same diameter in place of the aluminum fin. Okay, and here remember when you were telling that QF is proportional to d to the power 3 by 2, I'm meaning that the materials are same, meaning that everything else is just the same. Similarly, if I now have a fin of two different material but of the same diameter, I can say that my Q dot F is proportional to root over K. Okay, and then this is how you substitute the values of the thermal conductivity of aluminum and copper, and this is how what you will exactly get uh, from this. Okay, so that's it. So that's the answer. So that's the answer of the second part, that if you install a copper fin of the same diameter, you will enhance the rate of heat transfer by 1.29 or roughly 1.3 times to that of an aluminum fin of the same diameter. Okay. All right. So that ends the first question, and I'll again stop here for a couple of minutes, and then we will solve the second question of this exercise. Okay, so let's have a look at the second problem. In second problem, they're asking us to establish a relationship between fin effectiveness and fin efficiency. Okay, so let's look how the fin effectiveness and fin efficiency will, you know, so can we relate this fin effectiveness and fin efficiency, the two performance parameters of the fin? Okay, So for that, let's see first what is fin effectiveness. So as I said, we'll denote this fin effectiveness by epsilon f. And as I said, and as we just now saw some minutes back, that my fin effectiveness is rate of heat transfer from fin to the rate of heat transfer without fin. And if I just keep it as rate of heat transfer from fin, you need to understand that what will be the rate of heat transfer without fin. So for that, let's consider that let's say this is my usual wall that I have, and I have a fin, let's say, that is attached to this wall. Now rate of heat transfer without fin is the fact that, let's say, I don't have this fin in this cross sectional area, then my q dot without, that is if I don't have a fin, will just be equal to, so then what, so then all the heat from this area will basically be dissipated to the ambient. So this is just Newton's law of cooling. It is just h times the area of fin times theta b. I'm writing this is AF typically because I'm comparing that if I attach a fin here, but in the second case, if I don't have a fin in this area, what would be the rate of heat transfer? And then, sorry, I think I made a mistake. This would be AC, cross-sectional area of the fin. Yeah, so that's obvious, right? Because this cross-sectional area is AC, and I'm just saying that on AC, on this cross-sectional area, if I have a fin, what is the rate of heat transfer? To the rate of heat transfer, if I don't have basically a fin on this cross-sectional area. In that case, if I don't have a fin, my rate of heat transfer will just be h times AC times theta b, that is just from Newton's law of cooling, where theta b is just Tb minus T infinity, where Tb is the base temperature, and T infinity is the temperature of the cooling fluid. Okay, so this is the rate of heat transfer without fin, and this is just equal to H AC theta b. Okay, I repeat again, how did we calculate Q without, that is the rate of heat transfer without fin? So I am comparing a cross-sectional area where in the first case I will attach a fin, and then the rate of heat transfer is Q dot fin that I have said. In the second case, from the same cross-sectional area, I am saying that what would be the heat transfer if there is no fin. So if there is no fin, the area is then exposed to only the ambient, and the temperature of the ambient is T infinity with a heat transfer coefficient H infinity. Then the only mechanism by which this AC would dissipate heat to this surrounding is basically what would be the rate of heat transfer if there was without fin, which is equal to H AC times theta b. That is just simple Newton's law of cooling. We are just writing H A delta T, where A is now AC and theta b is just Tb minus T infinity, which is the delta T. Okay, I hope you understand this. Now, on the other hand, my efficiency of a fin is defined as the rate of heat transfer with fin, that is again the Q dot F, but this time it says that what is the maximum rate of heat transfer from the fin. So this is Q max from fin. Okay, now how do we calculate the maximum heat transfer from the fin? So you need to understand that under what condition the fin will dissipate maximum heat to the ambient. This is only possible when the entire fin is at the base temperature. Why? Because if the entire fin is at the base temperature Tb, then it have the maximum gradient in temperature between Tb and T infinity. In that context, if the gradient is very high, if delta T is very high, then you can have the maximum heat transfer from the fin. Okay, that's what thermodynamics laws in fact tells us. So the only way the fin can dissipate maximum heat is when the entire fin have the temperature equal to the base temperature, or you can say that theta is basically equal to theta b throughout the fin. Okay, which means that, so I'll write it down, that this the maximum heat the fin can dissipate is when the entire fin is at the base temperature Tb. Okay, Then, if then I write using this information, then what would be the maximum rate of heat transfer from the fin? So now the entire fin is at the base temperature TB, which means there will be no conduction taking place from the fin. The only mechanisms by which the fin can dissipate heat to its ambient is by convection. So then my Q max fin will just become H time. However, now I need to consider the entire area of the fin. Okay, that is typically because now the entire area is just at the base temperature. So then this becomes H times AF times theta B, and then this is Q dot fin. Okay, where AF is the fin area. This will take care of the cross sectional area AC plus the lateral surface area. Okay, of the fin, of course. Actually, there are two cross sections, or you can just say that the cross-sectional area plus the lateral surface area. So this is my second equation, which tells about the efficiency of the fin. Now, from the second equation, I can say that my Q dot fin. This is a very important conclusion, that my Q dot that the rate of heat transfer from a fin, this can always be written as efficiency of the fin times the maximum heat transfer from the fin, which is H times AF times theta V. Okay, and then if I substitute this, so I'll call this as, let's say, 2A, and if I substitute this 2A, that is the expression of Q dot fin, in 1 where there is also this Q dot fin in effectiveness, all I am doing is I'm just substituting 2A in 1, then you will simply see that your effectiveness is just Q dot fin, but Q dot fin is something that we have already evaluated from QA in terms of its efficiency, is eta F times H times AF times theta B divided by H times AC times theta B. This was, so H times AC times theta B was the case when there was no fin, basically. And then if you if you cancel certain things, if you cancel this theta B, and then if you cancel this H, then you'll get a nice little expression for, if you'll get a nice little effectiveness efficiency relation as eta F times AF by AC. So this is a relation, this is the important relation between fin effectiveness and fin efficiency. Okay. Oops. Okay, so that is what the question has asked us to find. The crux of this question is actually understanding how to calculate the rate of heat transfer without fin, and how to calculate the rate of heat transfer, how to calculate the maximum rate of heat transfer from the fin. Okay, if you understand this, then you can easily get the relationship between fin effectiveness and fin efficiency. I repeat, in case of effectiveness, we are trying to compare how installing a fin will is beneficial. I mean, we are trying to see why installing a fin is beneficial. In efficiency, we are trying to see what is that, given a fin, what is the heat transfer that will take place with respect to the case when the entire fin is at the maximum temp, when the entire fin is at the base temperature. Okay, so from this you can realize that your effectiveness will always be greater than 1 and your efficiency will always be less than 1. Okay, because I mean, for the use of a fin to be justified, if I want to put forward, okay, so I repeat, for the use of a fin to be justified, you want effectiveness to be greater than 1, and of course you want efficiency will always be less than 1, because this is an ideal case where the entire fin will be at the base temperature, basically. Okay, all right. Now, from the first statement that I said, that when, so there is a corollary kind of thing that you can say, that when is, if I ask you a question, when is the use of a fin justified, the simple answer that I would say is that its effectiveness has to be greater than 1, or else there is no point of installing a fin. This means if my effectiveness is less than 1, you are saying that your rate of heat transfer from the fin is less than to the case where there was without fin, which means what is the point of then installing a fin? There is no point in installing a fin there, because the objective of using fins is to increase the rate of heat transfer from the extended surface. Okay, So this means that I can now say from the definition of effectiveness that the rate of heat transfer q dot from the fin to h times ac times theta b has to be greater than 1. And let's say I consider the fact for a long fin. For a long fin, I already know that my q dot f is equal to under root of ph k times ac times theta b, which means if I substitute this here, you'll just get a relation basically. That's all. So this is just square root of ph kac theta b by hac theta b, and this should be greater than 1, which means that your square root of pk by hac should be greater than 1. Okay, that is the case, that is the scenario. I will call it as the scenario when the use of fin is justified, which means, let's say, so let's say I have k to the order of h. Okay, that is just for the sake of simplicity. In that context, I can say that my square root of p by ac should be greater than 1, which implies that my p should be greater than ac. And this is one of the crucial, design conditions when you are designing a fin. That is, the ratio of the perimeter to cross sectional area of the fin has to be very much greater than 1 for a fin to be effective basically. And that means that for effective fins, for effective fins, my p by ac ratio, this has to be very much greater than 1. Okay, in that context only your the use of fin is basically justified. Okay, and this, of course you can visualize also, because if you see, let's say you are seeing the fin of a bike engine, you can see that its cross sectional area is very much less, but its perimeter is very much greater. So one of the design requirements when you are designing fin is that your perimeter to cross sectional ratio has to be greater than 1, and that is again comes from the fact that your effectiveness has to be greater than 1. Okay, and that's why you basically see very, slender, I mean very thin fins. The width of the fin is very thin with respect to its length basically, because you are just maximizing the perimeter to cross sectional area ratio of the fins basically. Okay, all right, that is something I want to convey here. I'll stop here again for a couple of minutes. If you have any doubts, you can again ask me. But this is an important exercise that we did first in order to understand how did we define the effectiveness and efficiency, and second part, when is the use of a fin justified? What is the relationship? At least for a long fin, we have seen that this relation much hold good basically. Okay. All right. I'll stop here for a couple of minutes. If there are any questions, you can ask, or else we'll go forward and look into an important concept in the study of fins. This is known as overall fin efficiency, and this is more, a general. I mean, this is more, practically realizable thing, because this is actually where people use fin in actual engineering scenarios. Okay. All right. If no question, then we will look into an important aspect, I would say, in you know in fin literature, that is known as the overall fin efficiency. Okay, so normally until now what we have seen is that we have seen a base surface, and then from the base surface there is a single extended surface that we just now considered. Okay, for instance, a circular aluminum rod that is being attached to a wall, let's say, and things like that. But in reality what happens is, usually you don't encounter situations where there is just a single fin. Okay, so rather what happens is, like, there are multiple stacks of fin that are stacked together, and and you know and then this stack of fin is what basically is used to dissipate heat faster from the base surface. Okay, that is usually this configuration. So as you can see from your skin, there are three stacks of fin here, in addition to this, I mean, three stacks of fin that are being attached to the base surface basically. Okay, I mean, I hope you can you can see from the figure. So usually this configuration is preferred, typically because, like, you know, I mean, the efficiency basic. So in other words, I should say the overall efficiency which we are going to see, this overall efficiency gets enhanced. Okay, and uh, and that's the reason why we will define this overall efficiency, because this is a more practically desirable configuration rather than just using a single fin. Again, the fact that we want to minimize or we want to maximize the perimeter to cross sectional area, and because of which we are trying to maximize the number of fins that we can stack in this configurations. So you can interpret as something like that. Okay, so the manner in which this eta o, or the overall fin efficiency, is defined as the rate of heat transfer from the, so I'll call it as the rate of heat transfer from the overall, from the stacked fin, which is qt, to the maximum rate of heat transfer. Again, this is how efficiency is defined, right? Where this qt denotes the total heat rate from the surface at. Now then, what is at? At is the total surface which involves the fin area plus the bare area, or you can call it as the exposed area basically. So what the overall efficiency the overall fin efficiency says is that it is the rate of heat transfer from the total, I mean, the total rate of heat transfer to the maximum rate of heat transfer, where the total rate of heat transfer you know comes from the fact that this is the total heat transfer rate from the total surface at, which involves the fin area and of course the uh, bare area, which means this will involve the entire fin area, which is this, plus the bare area, which basically involves this. Okay, so if I want to quantify kt, if I want to see how kt look like, this will be number of fins times the fin area plus ab, where ab is just this bare area. I will, so this bare area, I will call it as this dotted portions, I'll call it as bare area. Okay, and the fin area is basically the hatched, this hatched portion is the fin area. Okay, I hope you can understand, this is basically your fin area. Okay, so then your n times the fin area, because this is your af, and the number of fins in general can be n, so n times the fin area plus the bare area will give you at, and the rate of heat transfer from this at is what we'll call it as qt, and we will see an expression to quantify qt. On the other hand, I can say that the maximum rate of heat transfer, qmax, will be the case. So the maximum rate of heat transfer Qmax will be the case when the entire assembly is at the base temperature. So this will just be equal to H times At times theta B. Okay, because this is when the maximum rate of heat transfer is possible. We saw that very recently, that the maximum rate of heat transfer is possible when the entire fin assembly is at theta B. So that's why we'll call the rate of heat transfer from that, which we are denoting as Qmax, is equal to H times At times theta B. Okay, then our efficiency eta O, it then just becomes Qt by H times AT times theta B. Okay. Now we need basically, so what is this Qt is something that we need to evaluate. Okay. So as I was telling you, this Qt is, I'll write it down for the sake of clarification. It is the rate of heat transfer from n fins plus rate of heat transfer from the exposed area. Okay. Then if I use this definition of Qt, I can call it as the n times rate of heat transfer from fins from a single fin plus the rate of heat transfer from the bare area, from the exposed area will just be equal to your, so what is the mode of heat transfer from the exposed area? It is just by convection, right? So this will be H times the area of the exposed area, we'll call it as AB times theta B, because you know that your exposed area, is at a temperature theta B, and the area is basically equal to the area is equal to AB. Okay. And the fluid has a heat transfer coefficient H, which means that the rate of heat transfer from the exposed area, which is basically this is HAB times theta B, and this is the first part that we are considering. This is the first part, that is the rate of heat transfer from n fins. Now in order to evaluate Qt, we now need to look what is Qf, because we don't know that what is the rate of heat transfer from each fin basically. Okay. And we are one assumption is that we are considering identical fins here. Okay. This is one assumption that we are considering. Okay. So I'll write it down that for identical fins, okay, my Qf, which is the rate of heat transfer from fin from the total n fins, is equal to n times the rate of heat transfer from a single fin, and then I can write this as n times, if I use the definition of fin efficiency of a single fin, it becomes eta f times h times af times theta b, because we are using the definition that my efficiency of a single fin is equal to the rate of heat transfer from a single fin to the maximum rate of heat transfer from a single fin, and then my rate of heat transfer, this is q, I'm sorry, I should write it as small q here because I'm using small q. Please don't confuse, these are just rates of heat transfer. So then the rate of heat transfer from a single fin is equal to your fin efficiency times the maximum rate of heat transfer from a single fin, which is equal to your h times af times theta b. This is when the entire single fin is exposed to the base temperature, and this is from where we are writing this. So this is actually from here where we are writing this expression. So this qf, that is the rate of heat transfer from the fin assembly, is n times the rate of heat transfer from a single fin, which is equal to eta f times h times of af times theta b. That's it. This means we have got an expression for qf. Now that's it. We just need to substitute this qf into this qt. So then this qt becomes qf plus this hab theta b, which is, sorry, yeah. So I hope you understand that this is the sorry. So this is the rate of heat transfer from n fins basically. So then my qt, that is the total rate of heat transfer, is just qf plus heat transfer from the bare area. I will call it as qb, q bare, and then this is n times eta f times h times af times theta b plus The heat transfer from the bare area is just HAB times theta B, okay, plus H times AB times theta B. Okay, so this is QT. Maybe I'll call it as some equation 2. Maybe I'll call this, okay, this was 2, so maybe I'll call this as 2, and then I'll call it as 3 maybe. Okay, and then your overall efficiency from 1 is just your QT by Q max, and your QT is N times eta F times H times AF times theta B plus H times AB times theta B by H times AT times theta B. Okay, so that's it. We can maybe do some cancellations. So this theta B and theta B would get cancelled, and then what, H and H would get cancelled, which means my eta O is N times eta F times AF plus AB by AT. Now the point is we don't know what is the bare area, right? So my bare area is not unknown, but we can calculate the bare area from the total area, because my AB will just be AT minus N times AF, because the bare area is just the total area minus the area of the fin area times the number of fins, basically. That's what we are doing. So then my efficiency will look like eta 0 will be N times eta F times AF plus AB is AT minus N times AF, okay, by AT. So you can write it down as, so if you rearrange it, you can write it down as 1 minus N times AF by AT. If you take this as common, it will be 1 minus eta F. That's it. So that is an expression. So this eta 0, eta O, which is the overall fin efficiency, is equal to the 1 minus number of fin times the area of each fin by total area, and this is 1 minus of efficiency of each fin. That's it. This is a useful relation in designing sorry, writing the overall efficiency of a, oops. So this is the relation which states the overall efficiency of a fin array. I'm sorry, it's just not forming. Yeah, I think this is good. So this is an expression for the overall fin efficiency. Okay, so so you can realize that this overall fin efficiency is written in terms of the number of fins that you are using times the area of each fin and the total area and the efficiency of each fin. So if you know this parameter, you can basically get an expression for the overall fin efficiency of the stacked assembly. Okay, so it just so for this we just need to know certain things, that how do we write the efficiency, that how do we write the overall efficiency, what is the maximum heat transfer from the stacked film, that is from the stacked assembly, and how do you calculate the QT, basically that is the total heat transfer from the fins and from the bare area. If you have this concept, then you can basically calculate what is the overall fin efficiency in this scenario. Okay. uh, I will stop here again maybe, and this is something that I wish to discuss, but maybe I'll give you a recap of fins, because this is an important concept. So we will once again look from where we started today. But before that, if there are any questions in this problem, you can let me know. I will be back by just filling my mug with some hot water. All right, guys, sorry for the interruption. So we just looked into how to basically calculate this overall fin efficiency. And so this is what I plan to discuss today. I hope this will help you to solve your assignment. There are a couple of similar problems in the assignment involving effectiveness and all those things, definition of fin efficiency, heat transfer from long fin and all these things. I mean, you should be now in a position to, tackle those problems confidently. So, so let's do a quick recap of what we saw today. So, so we began by actually trying to understand uh, heat transfer from extended surfaces. The reason why we were looking for extended surface is that why we usually look for extended surface is that we want to maximize the heat transfer, let's say from a wall or a slab. And one way of doing that, in addition to the convection loss, is by using an extended surface. And that is typically because diffusion also helps in. So the mechanism by which this extended surface work is, so this will diffuse the heat to this solid, and then this will dissipate basically the heat to the ambient. And that is in principle how a fin actually works. So for this we have defined a non let's say a scale temperature, I would say, which is theta x, which is just theta minus theta b. Sorry, theta minus, I would call it as, so we define the theta and I would call it as T minus T infinity, where theta was the temperature at each cross section in the fin minus the temperature of the ambient. So that is how we have defined the temperature how we have defined the variable temperature in case of a fin. And thereafter, we saw that the governing equation for theta is something like this. So it's a second order ODE, and then depending on the boundary condition you apply at the tip of the fin, you will basically get an expression for the rate of heat transfer taking place from the fin. For instance, if you have a long fin, you can say that your rate of heat transfer is something like this, which is under root of PHKC theta b. And let's say you have an insulated fin, the rate of heat transfer is this term multiplied by 10 hyperbolic ml. So if you kind of take the ratio of heat transfer from an insulated tip boundary condition to the heat transfer from a long fin, your ratio is just going to be 10 hyperbolic ml. Of course, it's going to be non-dimensional because it's a 10 hyperbolic function that we are writing here. Okay, but anyways, the point I want to make is that depending on the boundary condition you have at the fin tip, your temperature profile actually changes, which in turn changes the rate of heat transfer from the Fourier's law, basically. Okay. Now, the second thing we looked, which is an important aspect in fin design, is the fin performance parameters, which are fin effectiveness and fin efficiency. And we established an effectiveness efficiency relation, which basically looks something like this. That is 1 minus eta f times, I think it was AF by, uh, what was that? I think it was AC, it was something like this. So the effectiveness efficiency relation that we derived, yeah, it is sorry, I'm very sorry. So the effectiveness efficiency relation was eta f equal to, sorry, epsilon f is equal to eta f times AF by AC. So once you know the cross-sectional area of the fin and you know the fin area, then just by knowing either the efficiency or the epsilon would give you the other one. I mean, if you know effectiveness, you will basically get efficiency. If you know efficiency, you will basically get epsilon. Okay, that is how we get the effectiveness epsilon relation. Uh, but nevertheless, these two parameters are, as I said, these are known as fin performance parameter. And we saw that the use of fin is justified when effectiveness is basically greater than 1. And for that, we require a fin which has a very larger perimeter to cross-sectional area ratio. Okay, and this motivates the use of something known as stacked fin, because in place of using a single fin, if you are using stacked fin, exposing some part which are known as wear area to the ambient, this assembly is useful. And we have defined an efficiency using the concept involving this stacked film is known as overall efficiency. And then we looked into how do we basically calculate the overall efficiency of a fin assembly basically. Okay, and there we said that the overall efficiency is equal to the to the total rate of heat transfer to the maximum rate of heat transfer from the stack. and the total rate of heat transfer is associated with the total surface area that is available, which include the surface area from the each fin multiplied by n, which is the number of fin, plus the bare area, which is AB. This is the AT that we are writing. Okay, and then the maximum rate of heat transfer is when this entire stacked assembly is at the base temperature. I mean, that is how the Qmax is usually defined in case of a single fin as well. Okay, so from that we then try to calculate what is this Qt, which is just the summation of the rate of heat transfer from the individual fins multiplied by the number of fins plus the rate of heat transfer from the exposed area. And then the rate of heat transfer from the exposed area is the heat transfer coefficient times AB times theta B, and the rate of heat transfer from the fins is equal to the number of fins times the individual rate of heat transfer from each fin. And then we have used the concept of efficiency of a single fin to basically calculate this QF, which when substituted gives this QT, and then substituting this QT into this expression 1 will give you an expression for the overall fin efficiency, which is equal to 1 minus the number of fin times the area of each fin divided by the total area minus 1 minus eta f, basically, where efficiency, where I'll write it down that this that this eta f is basically the efficiency of a single fin. Okay, I hope you understand that. Okay, so you can try, so okay, so this is how the efficiency, overall efficiency, is defined. You can try a similar problem, I think, from so there is a problem involving this overall fin efficiency in your textbook. I forgot exactly the page number and uh, and the, I mean, the point where the problem is. But this is a good problem because if I remember, there was an engine. The problem was such that there is an engine, and you are trying to dissipate heat from the engine. So what you are doing is, instead of attaching single fin, you are using grooves, which are made of some material, and then you are, so the grooving is such that one assembly can be thought of as a single fin, and then you are attaching multiple assemblies by giving a certain, by leaving a certain bare area, and then then this becomes a fin stack assembly, basically. And in that problem you can uh, so the problem I was talking was something like this. You can find it in the book of Incorpora, but I don't remember exactly which page is. So the problem was like this. So you have an engine, let's say, of this form, and then you are trying to so this is just an engine that I am saying, that I'm drawing, and then you are trying to maximize the rate of heat transfer. So what you are doing is, you are putting some stacks of fin, something like this, and then this is just it's just an example that I'm drawing. So you're putting fin stacks like this on either of the sides. Okay, and okay, and then basically, so this will continue till, this distribution will continue till the length of the fin. And what you are doing is, and then there is this ambient air at T infinity, at H infinity, this is given. And then what you are required is that you are to see that how much, basically, I think, if I recall, they are asking you to calculate how much, how much increment is the rate of heat transfer, how much increment in the rate of heat transfer, rate of heat transfer that you would get if you don't use this fin. If there is no fin, just this bare, just this bare cylinder, then how much increment, how much, I mean, if then you are using fin, this stacked fins, how much increment are you getting, is something that they're asking in that problem. I don't remember the problem, but you can have a look at this book of, I mean, you can have a look at the book of Incorpora in the fins chapter, that is in terms from an extended surface. I mean, it was, so this is some engine of a motorcycle that is made of fins, like these stacked fins, and then it is releasing heat to some ambient, and the question is like that. Okay, so so that's what That's what the question was trying to find out. Anyways, so that's it, guys. So I hope with this, I believe that you can now solve the assignment based on extended surfaces. Just some couple of announcements. So the class on next Saturday, so I'll be traveling. So the class on next Saturday is postponed to September 5. So the class on third. So I mean the interactive session on 3rd August. It will be. It is postponed to 5th September. That I think it's a Friday. Uh, it's a Friday. So I think this is from 6 to 8 p.m. on 5th September. Uh, the scheduled class on from 3 to 5 p.m. On August is shifted to 5th September from 6 to 8 p.m. Okay, so I told you this verbally now, but you will a priori receive emails regarding this rescheduling, and also you will be notified in the discussion forum and the course website as well. Okay, so like mostly I'll be traveling, so it is likely that the class on 30th August is going to be shifted to 5th September, but as I said, you will be notified officially from the NPTEL team through emails, and also you'll be notified in the course website as well. Okay, but I have also stated it here as well. Uh, okay, so but apart from this readjustment, all other classes will be held on the usual timing. Okay, this is just for one session. That is the session on 30th August. Session on 30th August is going to be shifted to 5th September, but all other session will be on the usual timing. So I'll write it down that all other session will be on the usual timing, that is Saturdays from 3 to 5. Usual timing, that is Saturdays from 3 to 5 that we know. So this is just for 30th August, which is shifted to 5th September. And then all other classes will be on the usual timing. For instance, we'll have a class on 6th as well. Okay, because I think 5th September is a Friday. So we'll have another class. So we'll have two classes then simultaneously on 5th and 6th, and like that. So as I said, this readjustment is just for the class on 30th August, while all other session will be on the usual timing as we already meet from 3 to 5 on Saturdays. All right, guys. Then I will stop here, and I hope uh, you are being so I hope you are able to solve the problems of the assignment, and also going well with understanding the lecture series as well. If there are any questions, as I say, please keep posting in the discussion forum, and we'll be happy to address them. Till then, goodbye. We'll meet in the next class. That is likely on 5th September from 6 to 8. You will be notified by emails and also in the course website. All right. Thank you very much.